Thank you very much for the kind introduction. I know it's a long title, but I'll try to make at least in the introduction it's a bit shorter. So let's start with the motivation. I'd like to show you for the beginning 3 pictures. All of those pictures have at least one thing in common, and that's you have like parts that are mechanically loaded, and especially at a high temperature. So you have turbochargers, you have engines, or you have like power plants. And if you want to create such structures, you should know about the creep behavior of metallic materials. And unfortunately, most of those parts should last for a long time. But well, that's good actually, but it's bad for the determination of the material properties. So what is usually be done, you use instead of long-term experiments for 20 years, you use short-term experiments for like 100 or a couple hundreds of hours. And you try to extrapolate from your short-term experiments. But commonly, there is the Norton law used, and this comes with some problems, and I'd like to show you a different approach on how to calculate the failure time based on a different model. All right, that's the outline. So I already started with the motivation. I will follow with the experimental setup that we are using, because it's not standard, at least not from a tensile perspective, followed by the material model and the experimental results, and last but not least, the conclusions. The experimental setup. Commonly, the tensile test is used, but tensile tests are, well, you need a lot of material for that. And one of the major advantages of the small punch test is actually that you need a lot less material. You have a diameter of 8 millimeters and a thickness of 0.5 millimeter. And if you compare it to some common known objects like a euro coin, you see this is our little specimen. And we'd like to identify all the creep parameters based on those little specimens. Another advantage of those materials or of this test setup is actually that you do not need a large testing machine. So 1,000 or 10,000 kilonewton testing machine is totally sufficient. And for security reasons, it's also better because originally it was intended for testing of irradiated materials. And yeah, if you have less materials, you need less security measures. After the test, the specimen looks like this. And from there, we can conclude we have the problem of large deformation. But what does the test look like and how is it performed? The cross-section is shown here on the left-hand side. Our little specimen is located here with the little disc, and we apply a force on the punch, and a certain ball is pushed through the specimen. Yes, we have, of course, some names for each of parts. What's important is actually the lower part down here. That's a thermocouple, so we can calibrate our oven exactly to the temperature that we have at our specimen. And we can connect the thermocouple to a displacement gauge with which we can measure the deflection of the specimen. When you have your experiments performed, you have basically 2 choices. You can follow the standard where certain equations are given to correlate the behavior that you observe to some equation and to some measures that you have from tensile tests. Or you can do a different path, and that's what we are doing at our institute. And that's the inverse parameter identification. Basically, what it means is you do the test 2 times, one in reality and one virtually. And for that, you need, of course, a material model that can predict your behavior. And the parameter identification basically reduces the error between the 2 curves, one simulation and one the experiment. And you basically need the inverse parameter identification because the stress state inside of your specimen is inhomogeneous. So it's kind of hard to compare it, to correlate it to tensile data where you have a homogeneous stress state, right? Let's start with the material model. From the beginning or from the starting slides, you've seen, okay, we have large deformation. So of course we need finite strain. And we use here the logarithmic rate to end up with a hyperelastic formulation. And we assume that metals at high temperatures can be represented by linear elasticity, rate-independent plasticity, and viscoplasticity, in our case, primary and secondary creep. The linear elasticity is just Hooke's law, it's given over there. And the rate-independent plasticity is based on a von Mises type associated plasticity, also known as J2 plasticity, with an extended Vogt type hardening law that's shown, well,
Your finger is.
yeah, it's shown here, where you have like the initial yield strength and a linear term and an exponential saturation term. Here, all the equation you probably know, it's like a radial return mapping algorithm. And we use something similar for the creep model, as I show you now. The primary creep part is just a saturation term, where you have like two parameters, the epsilon star and the parameter p, where epsilon star tells you how much primary creep you have, and the parameter p tells you how fast you reach it. The second part is the most important part, because most of the specimen lifetimes is spent in the secondary region. And for that, I'd like to present a new model. And that is based on the time temperature parameter of the Larson and Miller. Formula for that is given here. And originally, it was used to extrapolate to larger failure times, or basically exchange time with temperature. So you do a test at a higher temperature, and based on the failure time you achieve there, you can calculate back to your operating temperature. To give you an example, basically you do two short-term experiments at lower or at higher temperatures, but at a specific load. You calibrate your parameter CLM, and then you can plug in your operating temperature and calculate your failure time. However, we like to implement this kind of method into simulation software. So what should we do? First of all, we need to get rid of the failure time and exchange it with the creep strain rate. And secondly, we need a stress dependence that I'd like to call stress function. The first part is quite easily done using the Monkman-Grant relation, where you have a relation between the secondary creep strain rate and the failure time, which again was originally used for extrapolation. If we insert that into the Larson-Miller time temperature parameter, and after some renaming of two constants, we end up with the equation over there. Last ingredient is the stress dependency, which is given as this equation. And unfortunately, I do not have the time to elaborate why we use specifically this equation. But there is a paper coming, so stay tuned for that. If we insert that into the Larson-Miller time temperature parameter and reformulate all of it, we end up with a creep strain rate equation, which we can plug into any kind of simulation software, which again is of the radial return mapping algorithm type. So, but this time without a yield stress. So, but I'd like to focus for now on the secondary creep part, and I'd like to give you an example for a different material. In this case, we have 63 experiments taken from literature over 5 different temperatures, and using the equation, this one, you can basically identify all the parameters that are inside. And using the formalism of Larson-Miller, you can project it onto a single line called master curve concept. But you can't see a lot there, so let me show you it in a different perspective. This is some common diagram in the creep community. So if you stress over failure time, and using just 3 parameters, it is possible to calculate the behavior over large stress and large temperature ranges. If you would compare that to the commonly known Norton law, you would end up with a straight line over here. And you would have to calculate or calibrate your material parameters for each temperature, because the parameters of the Norton law are temperature dependent and stress dependent. And basically, you can show that also in a different way. Creep strain rate over stress, Norton would predict here straight line. This is true for certain regions for single phase alloys, but in case of multi-phase alloys or large, highly alloyed materials, you always have a curved trajectory there. And using the model that I present here, you can actually capture that. Let's go to the experimental results using the small punch test. The constant deflection rate small punch test is similar to standard tensile test. You basically push your ball with a constant velocity through your specimen. You end up with the following curves for each of those temperatures. And using some nonlinear optimization techniques with a residuum containing all the available data that we have, you end up with these results. So the black curves are our simulations. And the parameter identification is done in a staggered scheme, meaning we start with the elastic parameters and continue with the plastic ones. Let's switch to the creep tests. They're not constant stress or constant stress state inside of your specimen, but instead they are constant force, because that's the only thing that we actually can do in small punch test. And our goal is that we do the test only to 100 hours because we're limited in testing time, and reload the specimen with a constant force rate. After experiments are performed, we end up with the following curves. And again, using nonlinear optimization and all the data that we can get from our test setup, we end up with the black curves. However, this time we have some deviation, mainly because of the failure time, which we cannot capture now, which is actually a large indicator that there's creep damage happening. So we need to improve there, because currently there is no creep damage happening inside of our material model. However, for the primary regions and secondary regions, it is acceptable. Which brings me to my conclusions. I presented a novel creep law for secondary creep that is based on a time temperature parameter and a master curve concept. And it captures the creep behavior over large stress and large temperature ranges. The implementation into simulation software is robust and successful. Rate-independent plastic behavior can be captured with the J2 plasticity model, and secondary creep can be modeled as well. However, failure times are currently not captured by the model, so this might be an indication for significant creep damage, which we are currently working on, as well as some validation tests using standard tensile specimen. With that, I'd like to acknowledge our project partners, especially in the area of Light Project H2Giga, and the scientific collaboration with Dr. Dimacek from the Institute in the Czech Republic. With that, I'd like to thank you for your kind attention.